Okay, welcome back. I know it's been like a century, like I might have even moved a little, but this time we are going to visualize some of that numeric data using the home loans data set that I talked about in the last video. Okay, so here are some of the ways to go about describing the shape of a numerical distribution. Just as a reminder, I know that we've all had a lot of statistics, but just so we are all on the same page. So we got shape. We got shape with skewness. We got right skewness, left skewness, as well as symmetry. If you want a refresher, I have a video that I make for my undergrads on skewed data. I find it helpful to think of the cowardly skier. So whichever side of the slope is steeper is the way the skier is not going to go. And so whichever way the skier goes is essentially how you name that skew. So if the skier goes to the right, it's right skewed. If the skier goes to the left, it's left skewed. Because the skew is the side with the longer tail. It's not where the lump of data are, as much as like that has been my instinct for ages. So yeah. Next, we have measures of central tendency, including mean, median, and mode. In general, these mean, median, mode, while mode is not always super useful, but together they also will tell you about the skewness of your data based on the ordering of the mean, median, and mode. If they're all on top of each other, that means you got a nice symmetric distribution. If they aren't, which is usually the case with actual data, the mean will be pulled further along the tail. So if you have right skewed data, the mean is going to be pulled to the right, more so than the median, because the median captures that 50th percentile point, where half your data are above that value and half your data are below that value. Medians are much less sensitive to outliers because they capture essentially rank order. And a bigger outlier is still like in the 1%, regardless of what the number is. It could be $1 billion, it could be $500 million. They'll still have the same pull on the median versus with a $500 million on the mean. You know, that's going to pull it, but not as much as $1 billion or whatever the numbers I've been using are. All right, so that's measure of central tendency. That's where the bulk of the data live. The spread is, well, describing how spread out your data are, like how much of them clump in that bulk. And you have range, which is essentially the distance between the biggest score and the smallest score. And that one is super duper sensitive to outliers because like it's literally outliers. That's all it is. While the standard deviation captures the inflection point of your distribution. It's the square, like this average deviation from the mean in your data. It's actually like the point of inflection on like a normal distribution. In fact, I don't think I'm going to animate that, but it's a thing. Last, we got interquartile range. Now that captures, well, the inner 50%. So it's much more robust to outliers than the range, because the range is like literally outliers, while the interquartile range is like where the bulk of the data live. So there's 25% of the data above the interquartile range, so in that 75th to 100th percentile, and then another 50 or 25% outside that range on the bottom end. Lastly, you want to look at your unusual observations. So these are your outliers. And again, you can catch some of these from raw summary statistics. Like you can get some sense of the shape of your data from how the mean, median, mode are ordered. But please, save yourself so much heartache and look at your data. Use your eyeballs to look at your data. That's like the whole mission of the class. Eyeballs. Data. Neat. All right. So here is one, we're going to go through some illustrations of different kinds of ways to display data. So a histogram is a little on the short side here. When I re-render the slides, it'll look lovely. But essentially, a histogram is a sliced up data set where you are counting within a bin range. All right, so here, fine, we'll fix this. Okay. We're fixing the data on the fly. Okay. Okay. So I'm just gonna pull. Oh, there we go. Let's do output with 50%. That should solve our. Okay. Yeah, I apologize that these are a little small, but such is life. You can make them as big as you want on your version. Okay, and you can even fork the slides and tinker with them yourself. Okay, let's go back to big screen. All right. Histogram. This is a way to capture the distribution of your data by binning it. Here we have mapped loan amount in dollars, and we haven't set anything here. We haven't done anything. And so it's set the bins to 30 bins by default. And it has essentially divided up the data into 30 separate chunks and is giving you the frequency count for each chunk. It's not super helpful. And we got this weird, like, giant pile, but it gives us a sense of what's going on. There seem to be some, like, super big ones, but a lot of the nuance is lost because it goes up to, like, 40,000 at least. So let's take a look a little deeper. We can break it up in bins of 1,000. Or set the bin width, I lied. Instead of, we can do number of bins, which is, or bin them by thousands of dollars, as I've done here with set bin width, where there are more than 30, but at least it gives you some kind of interpretable chunk rather than like having to divide the range into 30 bins. I don't like to do weird division like that on the fly. So I encourage you to do a bin width, because then you can at least see what the bin is, and you can see that there seems to be a really big popular amount right around $10,000. That's definitely the mode. But what happens if we slice it up into 5,000 bins of 5,000? We get a different kind of shape here. We've got a nice skewed data set where the mean, the median, the mode, and probably the mean are right around 10 grand. Well, the mean's a little higher than 10 grand, but different binnings give us a different slicing of the data. It doesn't change the fundamental nature of the data underlying it. However, various, depending on what kind of information you want to convey, you may choose different bins. And then there are some bins that are just utterly useless. like this one, bins of 20,000. Really, and when I say utterly useless, sure, if you have a really refined amount of space, but my point is that you can bin at different ranges to describe your data. Okay. We can do some cool customizations in histograms, as we can see in our plot here. So even with the bin width of 1,000, we can add, for that 5,000 bin, we can update our labels. As I've shown you this with the penguin data, but we're gonna show you again, because you can customize lots of different types. Now here we've got Geome histogram, and I've highlighted successfully this time the lab space, where we've got X, loan amount in dollars, Y is the frequency count, and title is amount of lending amounts of lending club loans. Label your graphs. It'll help you later. We can do some cool stuff like fill based on a categorical variable. So here we've set the fill color as a function of home ownership. Ta-da! And it gives us essentially a stacked bar plot. We can see that a big chunk of folks either mortgage or rent. Not a lot of folks own. These histogram pieces are additive. And it gives you a sense of where the distribution is, while maintaining the underlying information from the histogram itself. Does this kind of description, this plot, have some problems? Yeah, because it can be misinterpreted pretty easily, and you do have to kind of, if you're interested in only one of the distributions, you have to kind of manually adjust each piece to compare across. So an alternative is to facet by a categorical variable. And this is the exact same data. It can show you without having to visually update it. And I encourage you to play with this plot data on your own, because I know that these slides aren't the best at showing this at the moment. But we can just see the sheer number of rental lendings as well as mortgage lendings versus the people who own their home outright. They don't seem to get a lot of loans. Next, density plots. So just a basic density plot, looking at loan amount by density. We can adjust the bandwidth for density plots in the same way we can adjust them for histograms. Like a density plot, you can kind of think of as a smooth histogram. The default is 1. Fun facts. You can kind of smooth it out if you want to have a nice spiky one to show lots of different changes, smaller bin width, or smaller adjustments versus larger adjustments, smooth it out. So we can customize density plots as well, where we have our x-axis loan amount in dollars, y-axis is density, and update the title. We can also add a categorical variable here. I apologize that this is small. Let's just fix that now. Okay. Adding a categorical variable. Oh. Okay, so what I'm going to do is make a output with. Output with, see if that helps. And then it'll re-render. Maybe. But you can see here what I'm doing is I'm printing out. We're gonna not, let's, okay, what happens if we make this 100? All right. As you can see, the perks of dynamic plotting is I'm allowed to tinker with them on the fly while recording. But at the same time, that also means that I can tinker with them on the fly while recording. It's a gift and a curse. Okay, we made it a little bigger so you can like actually see it. Okay, let's go back. Here we go, Zoom viewer. Cool. So here, under the geom density, we've made 3 changes, and I've highlighted. First, we've set the fill for home ownership, and we have also, here's a really important thing to make sure you do when you have a fill like this for density plots, because they're displayed side by side. You want to set your alpha to be less than 1 so that you can actually see the 3 of them through there. And for labels, we've added a label for fill with a nicer title. Next, box plot. A box plot is a way to describe the distribution of your data. This one's on its side, as it highlights so here's what a box plot is. So this is John Tukey's. I'm like 95% sure he invented this because he invented all the things, but it illustrates the distribution of your data with a 5-number summary. That big white bin in the middle, that's where 50% of your data live. And the edges there capture, I think it's the trimmed range, versus those little dots at the end, which capture the outliers. I encourage you to explore the documentation to get a better sense of this yourself. But as you can see, the bulk of the data are in this chunk. And, okay. Oh, this is interest rate. Okay, here we go. Nope, not gonna tinker with it. Not gonna tinker with it. You are welcome to on your own time. But here we can adjust our labels. We can remove a label like Y, we can set it to null. But we can also add theme. So we can blank out various things. Like here we've cut out the axis ticks and just set those to blank. Because we don't need them, they're not very helpful. And less is more. All right. We can also add a categorical variable here where we will plot or break down our histograms by grade. So set your Y aesthetic to what you want to break it down by. Here, grade is a categorical variable, so it does it nicely. And I recommend adding a subtitle to describe what's happening. So as you can see here, there's a pretty nice relationship for the most part, pretty linear, where low interest rates are A grade, up and up and up, and when you get to like G and F grade, we're in like 30+%. We're in loan shark territory. But, I mean, it makes sense because these are the loans that aren't being done through banks. They're being done through kind of individuals. But it's good to get a sense, and it also shows us pretty clearly where the outliers are. It's all in the G loans. Okay, almost done, I promise. Relationships with numerical variables. So we can do a scatter plot here. And what I can't show you is the interest rate as a function isn't a huge function. It's pretty linear for debt to income ratio. Most folks have a small debt to income ratio, while a couple have huge debt to income ratios, but it doesn't seem to be a function influence much of interest rate. However, there's big chunks here that are missing, and so I would suspect that this missing information are folks that want, like, this could be loans that aren't approved. So missing data can be informative, but we don't have that data in front of us, so we don't actually know. Here is a hex plot with a similar thing. It captures kind of the counts within a little hexagon, as opposed to the scatter where it's literally on top of each other, so we can't tell how many dots there are or how many people per dots. We can only see that there happens to be someone who exists in that chunk. And the hex gives us kind of a sense of the density of that area. We can also filter by kind of do a subset of our data that only looks at debt to income ratio below 100. Not that you can see that, but you will have to believe me, it is in the slides. So that's it for this video. After this, I will be fixing the slides. But I'll see you later. Bye.